Hi everyone, this is Ms. Shea. In this video, we will be looking at covalent bonding. After watching this video, you will be able to define the term covalent bond, differentiate between single, double, and triple covalent bonds, state how bond length and bond strength are affected by the number of electrons shared by two atoms, and deduce the polarity of a covalent bond from electronegativity values. A covalent bond is defined as an electrostatic attraction between a shared pair of electrons and positively charged nuclei. It is formed when two nonmetal atoms share a pair of electrons. Both atoms achieve noble gas electron configurations by sharing the electrons. Generally, we say that when the electronegativity difference is less than 1.8, then a covalent bond occurs. However, it is better to just remember that a covalent bond occurs between two nonmetals. Covalent bonds may be single, double, or triple bonds. This depends on how many electrons are being shared between two atoms. A single covalent bond occurs when one pair of electrons is shared. A double bond occurs when two pairs of electrons are shared, and a triple bond occurs when three pairs of electrons are shared. The strength of a covalent bond is measured by the bond enthalpy, which is defined as the amount of energy required to break 1 mole of a bond in gaseous molecules. The bond enthalpy increases as the number of shared electrons increases. This is because as the number of shared electrons increases, the attraction between them and the nuclei of the bonded atoms becomes stronger. This means that for the same pair of atoms, a triple bond between them has the highest bond enthalpy, followed by a double bond, and a single bond has the lowest bond enthalpy. In other words, the triple bond is the strongest, followed by the double bond, and the single bond is the weakest. This pattern is seen in this table with the bond enthalpy data of carbon-carbon single, double, and triple bonds. The bond length is defined as the distance between the nuclei of two bonded atoms. The stronger the bond, the closer the bonded nuclei are to each other. So for the same pair of atoms, the single bond, which is the weakest, has the longest bond length, followed by the double bond, and the triple bond, which is the strongest, has the shortest bond length. We can see this pattern reflected in this table with the bond length data of carbon-carbon single, double, and triple bonds. A covalent bond can be polar or nonpolar depending on the electronegativities of the bonded atoms. If they are identical or have similar electronegativities, then the bonding electrons are shared somewhat equally, and there is no tendency for the electrons to be closer to one nucleus over another. So the bond in this case is a nonpolar covalent bond. If the bonded atoms have very different electronegativities, then the bonding electrons will be more attracted to the more electronegative element. In this case, a dipole, or a separation of opposite charges, is established, and a polar covalent bond is formed. In this picture, we see an example of a polar covalent bond in the HCl molecule. The distribution of the electrons is uneven. Because chlorine is more electronegative than hydrogen, the electron density is greater around the chlorine nucleus. This can be shown with a vector pointing towards the chlorine atom, such as the one shown in A. Or we can show the positive and negative charge distribution with the Greek letter delta, followed by a plus or minus sign. This is shown in B, where delta plus indicates the partial positive charge of hydrogen, and delta minus indicates the partial negative charge of chlorine. Here we see a representation of the electron distribution in a nonpolar covalent bond, a polar covalent bond, and an ionic bond. The electron-rich regions, which are negatively charged, are shown in blue, and the electron-poor regions, which are positively charged, are shown in red. In the nonpolar covalent bond, the electrons are evenly distributed between the two bonded chlorine atoms, and there are no charges on the atoms. In the polar covalent bond, the electron distribution is asymmetrical between the two atoms, and a dipole results. In the ionic bond, there is a full positive charge on the sodium ion and a full negative charge on the chloride ion. We can tell whether a covalent bond is polar or nonpolar by calculating the electronegativity difference between the two bonded atoms. If the electronegativity difference is below 0.5, we would consider the bond to be nonpolar covalent. If the electronegativity difference is from 0.5 to 1.8, then we say that the bond is polar covalent. And if the electronegativity difference is 1.8 and above, then we say that the bond is ionic. However, the boundaries between the different bond types are actually pretty fuzzy, and it is actually more useful to think of bond types as a continuum of electron distribution instead of distinct types.